Hello Internet, my name is Quinn and this is Blondihacks. This is part 3 of the lathe-only first engine build that I'm hoping you will try with your shiny new lathe. Today we're going to make the crankshaft and the flywheel. These are pretty simple looking parts, but it's lots more excuses to show you some lathe techniques. So let's go. Our wobbler is looking pretty wobbly, but it needs a crankshaft right there. Here's the crankshaft that we're going to build for this engine. It's made in 3 pieces. This could theoretically be turned out of one solid piece, and I did actually consider that in the interest of keeping part count low, but making it with 3 pieces, the orange pieces being drill rod, makes this much easier to build, and that is of course the goal for this first engine project. I'm going to start by making those orange drill rod pieces, once again starting with precision ground 01 tool steel, which is what we mean by drill rod, at least in North America, and these are very trivial parts, just face them down to length. The lengths on these parts are not overly critical. If they're longer than shown in the drawing, that's totally fine. Lots of wiggle room there. The other reason to use drill rod, of course, for these is that it's precision ground, and so it has very nice surfaces on it, because the surfaces of all of these pins are going to be the bearings, effectively, of our simple little engine. With the crankshaft and crank pin finished, I'll move on to the crank web, which is the disc that connects them. And that disc is going to be made out of this ratty old chunk of round bar that I found in one of my scrap bins. This can be any kind of steel, really. Doesn't matter very much about the alloy. This happens to be 1018, which doesn't machine very well. I would recommend buying something like 12L14 or 1215 or 4140, a nice machining steel if you're a beginner. Makes this job a little bit easier. So I will face off the end, of course, as is tradition. Then I will turn the OD of this to the dimensions specified in the drawing. So far so easy, right? Nothing to it. Now this is actually a very simple crankshaft. The crankshaft on any engine build is frequently the most difficult component because they can be quite intricate indeed, but this little wobbler has just about the simplest form of crankshaft you can have. Once I'm happy with those dimensions, I'll put the center bore in it for the crankshaft. I'm going to center drill, and ream this, which will be reasonably concentric. Ideally, you would want to bore it, but for the crankshaft, this is plenty. The crankshaft doesn't actually have to be perfectly concentric with the OD, because the OD isn't actually doing anything. What matters is, of course, the relationship between the center bore and the crank pin. Let's talk about that crank pin now, because it's time to make the hole for it. As you can imagine, that is the trickiest part of this component. In particular, as you've probably already assumed, the distance between the crankshaft and the crank pin from center to center is the most critical thing on the crankshaft. It's always important on an engine, of course, but particularly on a wobbler, because not only is that setting the vertical travel of the piston, but it's also setting the alignment of the valves. The throw of that crank laterally has been calculated to match the distance that the valve port on the cylinder travels as it swings back and forth around the pivot. Of course, that dimension's given in the drawing. You don't have to calculate it, but you do need to ensure that you put that hole the right distance away from the center bore. What we need to do here is what's called eccentric turning. That is, lining up something round such that the center of it is not what's centered on the lathe. Now you can do that with layout and dialing in the dead center, as I've shown in other setups like we did on the cylinder where we had a punch mark that was laid out. And this works great when you've got an odd shaped part like that cylinder. And you could do that here. However, there's another way to do it when you've got a simple round part. It's often quicker. We can dial in the eccentricity we need directly in the forejaw using an indicator. So I'm just touching up my indicator with a little bit of preload on 0. Then without moving that indicator, that's important, don't move it, use one pair of jaws opposite each other to dial in the eccentricity that you want. Now we're measuring radius here, so for a 400 thou crank throw, which is what we have, we want to see a 400 thou deviation on that indicator from one side to the other. Now when you think you've got it or you think you're close, we can do a different measurement to confirm that. In this case, what we're going to do is touch up the indicator on the low spot. So we're going to find the low spot by rocking it back and forth and then zeroing the indicator on the low spot. And then we want to swing it around to the other side and watch the travel on the indicator. Now in this case, we're measuring diameter, not radius, so we want to see twice the distance on the indicator for the amount of crank throw that we're looking for. So in this case, I've got 4 laps of that indicator, so this is 400 thousandths between high spot and low spot. Again, rocking it back and forth on the high spot to make sure you're on it. So that's 400 thousandths. However, if you're paying attention, you know that should be 800 thousandths because we need twice the throw on this measurement because this is the diameter measurement. And here's where we get into trouble with this method of eccentric turning. If you get too far offset, then the other pair of jaws, top and bottom, start to lose their grip on the round surface. What's shown here is about as far as I would go, because if you go any further than that, there is a little zone at an angle where the part can squip right out of there. This squip zone is defined by a ratio between the amount of eccentricity you're trying to create and the radius of the part. Somewhere around 50% is about as far as I would go. So this is 50% right here. I've got half of the eccentricity that I want, or half the diameter of my part, give or take. You'll know if you push this too far when you wake up in the ambulance and the paramedics explain to you what happened. So what do we do about this? Well, remember that ratio I talked about of eccentricity to radius. We don't want to exceed 50% there. So since we can't change the eccentricity that's set in the drawings, we can change the radius. We can make the part bigger. We can create an offset turning jig, which is essentially a virtual part that is larger that will hold this part at the correct offset while staying out of the squip zone. Here's a nice aluminum disc I found in my scrap bin, machined on both sides. And I'll put that in the forejaw, and I start by dialing it in, and then I once again touch up the indicator. You can see I've also turned a reference diameter on it, and then I do the same eccentric dialing in that we just did with the part. Again, not moving the indicator from its initial position, and dialing in a high spot to match the radius of the eccentricity that we want. Then once again finding 0 on the low spot and measuring the diameter of the eccentricity. So in this case, you'll see this needle go around 1, 2, 3, 4, 5. Shift my hand. Dramatic 6, 7. And again, finding the high spot on 0. And, oh, too far. Wiggle back and forth to find the high spot, and that's 8 right there. So that's dead nuts, 800 thousandths of eccentricity on the diameter. Then what we do is we turn a counterbore into the face of this disc of aluminum, and the result is going to look something like this. Our crank disc will slot into that pocket that we've machined, and you can see there's a little threaded hole on one side that we can put a set screw in to hold the part in place. You could also probably use super glue, you'd probably get away with that. And then if we look at this setup from face on now, you can see that centroid is the center axis of the lathe. So when this offset drilling fixture, the big orange disc, is dialed in concentrically on the lathe, it's going to hold the little green disc, which is our crank web, at the correct offset, and that centroid is where the crank pin is going to end up. And then that distance is the 400 thousandths that we need. And because the larger disc is dialed in concentrically, there's no weird jaw offset happening. We don't even have to think about the squip zone because all of the offset's being created by the jig. So this is a very safe way to do it, and you can do any amount of offset on any part really with this kind of thing. Now I'm actually not going to do this here because honestly I don't want to waste that really nice disc of aluminum that I'm going to use for something else. So I'll show you another way to do it. I'm going to flip the piece around, we haven't parted it off yet, and I'm going to hold the machined end in the chuck to make sure that it's square to the jaws, and then I'll face the end of the rough cut bar. This is to give me 2 parallel surfaces at each end of this rough cut bar, and that's going to give me a reference to hold this piece vertically over in the drill press, which is where I'm going to do this hole. So I'm going to lay out the position of the hole. I'll set my dividers to the offset that we need for the crank throw, and then I turned up this little button that's going to give us access to the center of that bore, and then I can use my dividers to lay out that radius that we need, and then I'll put a center punch anywhere on that radius, and then I'll line up that punch mark over on the drill press. I'm going to hold the piece in my float lock vise because that allows me to reference it down on the surface of the table. That's important. Don't put it in any old cheap drill press vise because the top and bottom surfaces of those vices are generally not very parallel. You want the end of the piece referenced on the table. So I don't expect you to have a fancy float lock vise, but you can C-clamp it or strap clamp it down to the table using the T-slots. This is important because we want to squeeze as much squareness out of the drill press as we can. This crank pin obviously needs to be square to the face of the crank so that the connecting rod will run square in the engine, and the drill press can do a good enough job of this if we're very careful with how we set it up. The lathe is always going to be better if you can. You're going to get more squareness out of a lathe than you are out of a drill press, but we can do okay here for a simple engine like this little wobbler. As I've said a lot, these engines are pretty forgiving. That was drilled and reamed then to the crank pin size, and that is looking pretty good. Back over to the lathe now, and we can turn the little hub that's on the back of the crank web. The purpose of this hub is to lower the friction between the back of the crank web and the front face of the frame, where it's effectively riding on that as a bearing. All that's left then is to part it off to width. And in order to do this accurately, I'm going to set my parting blade on the front surface of that crank web using a dial test indicator on it, which tells you exactly when that parting blade is touched off. This is a trick I got from Stefan. Thanks, man. It's a great way to do this. When you get to the point just before where that indicator is going to start moving, you know you're perfectly touched off, and then you can calculate the width of your parting blade plus the thickness of the part that you need and translate over that amount. The thickness of the crankshaft is fairly important because if it's too thick, then it's going to bind up with the piston, which is expecting to be on a certain axis, of course, aligned with the cylinder bore. So if you're going to make a mistake, make it a little on the thin side, if anything, but the engine will run better if it's the exact right distance because the crank web provides a little bit of a bearing surface for the connecting rod on the piston. Time for final assembly on the crankshaft. The crankshaft itself gets Loctited into the crank web, and that is given lots of time to cure. Wipe off the excess, of course, and then once that's cured, I flip it over and I Loctite the crank pin in to the crank web. Make sure they're facing opposite ways out of the crank web. Yes, I have done that wrong on occasion. This is Loctite 680, by the way. 603 would also work in this case, both permanent retaining compounds. Once that's cured, then our crankshaft is ready to go in the engine. It's looking pretty nice. Now then, on to the flywheel, which is the next major component to make. And the flywheel is just a great big chunk of metal. Its purpose is to smooth the top dead and bottom dead center zones of the engine where the physics of a reciprocating engine kind of fall apart. It's like a mechanical capacitor stores a little bit of energy to carry it over between valve events. I'm going to make this from this big steel slug that I've cut off a big chunk of round bar on my horizontal bandsaw. You probably don't want to order a huge piece of round bar just for this part, so if you're ordering materials for this engine, you can order little discs like this from a lot of the online suppliers. I'm going to start by facing off the front as is tradition. I'm going to get our first reference surface on the flywheel. Next, I'm going to cheat a little bit and I'm going to cut the hub on the back of the flywheel now in this setup. And this is cheating because for best possible results, you should actually do this at a later step that I'll talk about more later. The way I'm doing it here, we're going to lose a little bit of concentricity on the cosmetic outer surface of the hub, which sometimes you can see when the engine is running, but it's not going to affect the function of the engine. But just something to keep in mind. I'm doing it this way because it's frankly a lot easier to do it this way, and for your first engine, you should focus on the easiest way to do all of these steps rather than, necessarily the absolute best way. Again, the goal of this entire project is to leave you with a running engine, not the prettiest or the best possible engine, or the most efficient for that matter, just one that runs. If you're trying to do this on a 7x14 mini lathe, you may want to make this flywheel out of brass. That will work just as well, and brass is going to be a lot easier to make in this case because there is a lot of heavy turning, a lot of material to remove on the flywheel, and if you're using a tiny lathe that can only do really light cuts in steel, you might be here all day doing this. Once that's done, I'm going to drill and ream the center bore, and this is why I was cheating by making the hub early. Because we're drilling and reaming, we're not using a boring bar, we're not guaranteed to end up with a concentric hole. So the hub might actually have a little bit of run out relative to this center bore. But as I said, it's only a minor cosmetic thing because we're now going to take the part out and we're not going to turn the OD yet. More on that in a second. I'm going to flip it around and I'm going to tap it in against the face of my chuck with some parallels, and we're going to face the other side down to final width. That's again easier to do in the chuck while we have it with a good grip on it, And again, we have a lot of material to remove because this disc is quite a bit over thickness in my case. The parallels and the tapping in were important to make sure that the front and back faces of this part end up perfectly parallel. Although again, that is just a cosmetic thing, and if you have a little bit of parallelism error between the front and back of the flywheel, you might be able to see it when the engine is running, but it's not actually going to hurt anything. Once again, if you want to make the best possible flywheel that you can, then you would not do any of these steps in any of these setups. You would only do the bore, and you would save all the rest of it for the next setup that I'm about to show you. You can also see I didn't dial it in radially. You can see the bore running out in this shot because we're just doing facing cuts in this setup, so that doesn't matter. All right, once that's faced down to width, now I'm going to take this out of the four-jaw chuck, and we are done with this for now because the rest of the operations are all going to be done by turning this on a mandrel. In my case, I'm going to use the collet chuck and in this piece of scrap round bar that I found in the bin, but in fact, you can actually do this in your three-jaw chuck. It doesn't have to be a fancy chuck, as long as the amount that you're removing from the mandrel is more than the runout in your chuck. And then once you've turned this mandrel, do not touch anything in your setup. Don't move it in the jaws, don't loosen the jaws, and it will be perfectly concentric. So I've turned tail support for this because we're going to need it in a minute, and I'm going to turn down this mandrel to the size of the bore in the flywheel. I want this to be a very close fit, as close and accurate a fit as you can get. The better this fit, the more accurately your flywheel will be turned, and the smoother and nicer it will run. Once the diameter is good, then I'll put a little Sharpie on there because I'm going to turn down the outer portion of it a little bit more so I can cut some threads on it with a die. And the Sharpie just helps me see where the reduced diameter area is so that I know where to stop with the die, because it can be a little hard to see when you're talking about, very tiny diameter differences on the part. These threads need to be long enough so that they extend slightly into the bore on the flywheel so that the nut that we're going to put on the end is going to clamp tightly against that flywheel. The idea is that the nut is clamping the flywheel against that shoulder that we've turned at the back. You cannot clamp it against the face of the chuck. That's just going to pull the mandrel out of the chuck. And you can see I've got a copper washer there under a normal washer so that I can get a nice tight grip without damaging the face of the part with a steel washer. And we gronk that down and put the tail support in the end, and away we go. Now everything that we turn is going to be referenced from that mandrel. And this is how you get the perfect running flywheel, because of course that bore is where the crankshaft is going to be, so we're effectively turning the flywheel on its own crankshaft by doing this. And this is also why the hub is running out a little bit, because I didn't turn it in this setup. If you wanted to make it as perfect as possible, you would do all of the cuts on the flywheel in this setup. But some operations like facing on a mandrel can be tricky to do well, so I'm showing the easiest way that I know to do all these steps, not necessarily generating the best looking result. But this will still look nice on the engine, as you'll see. Now we need to make the little set screw that's going to hold this onto the crankshaft. Over to the surface plate to mark the center of that hub, just so the set screw kind of looks nice. You could also eyeball this, and frankly it would be fine, it'll function. Then I take this over to the drill press, and I'm going to set this up in, again, my float lock vise with some copper to protect our finished surfaces from the vise jaws. Now to line up horizontally on the top of that curve, we're going to use an old model engineers and fabricators trick, which is to balance something flat on there. In this case, I'm using a thin parallel with something pointy, in this case a center drill, and you shift the part back and forth until that long flat thing is sitting horizontal. And then I make sure that I'm also lined up on the other axis with my scribe line, and then we know we're centered and at the top of the curve, and I lock it down when I'm happy with that. And then I can center drill that. The purpose of the center drill is, of course, to keep the drill from wandering, because the drill will slide off of a convex surface, but the center drill won't, so it creates a little dimple that allows the regular drill to start on target. So we drill that in through to the bore, and then I'll use the drill chuck to tap that hole. Regular viewers know I don't love tapping this way, but on the drill press, if you're not using your milling machine, this is definitely the easiest way to do it. You don't have a lot of feel doing it this way, so be careful doing that with small taps, but that worked out just fine. And then our little set screw can go in there, and this thing is ready to install on the crankshaft. Of course, there's lots of opportunity here for decorative touches. You could trepan some nice grooves or drill some holes to make it a little bit spokey or whatever you want, but the solid one will work just fine also. Let's get this all assembled now. The crankshaft goes through the main bore on the frame. I've got the frame screwed to a piece of wood. Now the crankshaft needs a flat spot for that set screw to sit on. So I'm going to put some Sharpie on the crankshaft, and we slide that on and position it so that the crankshaft has a little bit of end float. You don't want it squeezing tight. And then snug down that set screw, and it's going to make a mark in that Sharpie so that you know where the set screw is going to be sitting on the crankshaft. You never want a set screw to be clamped down on a round shaft for two reasons. One, you're only relying on friction then for the hold, which is never going to be very good, especially on a tiny set screw. And two, when you gronk down on that set screw, it's going to mar up the shaft, and you won't be able to remove the flywheel in 6 months when you need to. A little flat spot solves both those problems. Keeps the shaft from getting marred up, and when you've got a set screw clamping down on a flat spot, that's a geometrical mechanical hold, not solely a friction hold, so that flywheel cannot come loose unless that set screw moves. Little test whirl, and that looks really good. The frame is flexing a little bit on my block of wood, but otherwise that looks like it's running very, very true. So our efforts on the Mandrel were efforts well spent. It's actually running really beautifully in there. It should be a nice running engine once we get a few more parts made. We are almost there, but that is all the time I have for you this week. Thank you so much for watching, and thanks to my patrons for making this all happen, and I will see you next time.